So over the last few weeks, we've been learning how to do thermodynamic analyses of closed systems. And that's pretty much the stake in the ground for what we're going to learn on the first midterm. So now's a pretty good time to do a review of what we learned so far. So this is how you do closed systems in thermodynamics for mechanical engineers. So what are the topics that we want to review for the exam? First, we learned about basic principles, units, the difference between mass and weight, and how those units can be difficult in imperial systems, problem-solving methods for engineering classes. We learned about pressure and the different kinds of units for pressure. We learned about work and power in different heat transfer modes. We learned about the first law for closed systems. We learned how to do specific heats for solids and liquids, and we learned how to deal with ideal gases. We learned how to find thermodynamic data in tables for subcooled liquids, two-phase mixtures, superheated vapors, and ideal gases. We learned how to interpolate and how to do double interpolation, and we learned some strategies for how to avoid double interpolation too. We also learned how to find properties like specific volume and specific internal energy without a table when we're looking for incompressible liquids and solids and ideal gases. Before the class even started, we learned lots of different definitions, so you need to review those terms and all the other definitions that we've learned since then. We've learned about things like properties and units. We have knowledge of properties used in thermodynamics, and we have an understanding and appreciation of units. We understand both SI and imperial units. And while the type of material we learned in week 1, or even before the class, is really multiple choice type questions, it might not just be definitions. There might be some small worked out problems on the multiple choice from this section as well. Remember, we learned about manometers and mass versus weight. This was a good way to learn about unit conversion. So we know that the pressure difference in a manometer here comes about because of the weight of this water above this plane. We know that in metric units, the change in the pressure is equal to the density times the acceleration of gravity times the height, which is the volume divided by the area. So that's rho g L, where L is shown in this figure here. Now, of course, everything's always more difficult with imperial units. And in that case, anytime in an equation you see G, your spidey sense should start tingling, right? The hairs on the back of your neck should stand up, and really that G then gets replaced by G over GC because it's not acceleration of gravity, it's the relative acceleration of gravity because pounds are pounds here on Earth. We learned about conservation of energy for closed systems, where we have the change in energy in our system over time is equal to the heat transfer in minus the work out. We learned how to find work using this equation, the integral of P dV. Now, if I show my process graphically on a PV diagram, one of the reasons we like these PV diagrams is that when we plot out our process, then work is the area under that curve. That's P dV. In order to do this calculus, we want to see that P times V to the power of N is equal to some constant. So I need to get P as a function of V. So I would take an equation like this, PV to the N is a constant, and divide both sides by V to the power of N. So I get a relationship for pressure as a function of volume. I put that into my integral, and then I'll get one of several different answers depending on my pressure-volume relationship. Then we started to say, okay, well, work is one of the things that we need to find our conservation of energy, but we also need to know about the change in energy in the system and the heat transfer. So we turned our gaze to this change of energy in the system. And we learned that this change of energy is the change of all the different energies that we could see in the system. The change in kinetic energy, the change in potential energy, the change in spring energies, and the change in this new kind of energy called internal energy. And it turns out that in thermodynamic processes, or at least the ones that mechanical engineers tend to look at, it's usually the internal energy that dominates the problem, so that delta E can become delta U. So for our first law, we usually don't know how to find heat transfer, not until you're a third-year mechanical engineering student. So work we find as the integral of P dV. Delta U we find as m times delta little u, where little u is specific internal energy. That's the kind of energy we can look up on a table if we know the state. And then we'll use our knowledge of work and delta U to find heat transfer. We find delta U either from tables or by using specific heat relationships. In particular, because we're looking for delta U, we would use CV times delta T. That's the specific heat at constant volume. There's other ways that we can find delta U, so we need to know what is the fluid. And when the fluid is water, there's a second part of the question that we can ask, and that is, what phase of water are we talking about? Do we have only liquid water or subcooled liquid? Do we have only steam or water vapor or superheated vapor? Or do we have some combination of these two things under the vapor dome? So do we have a two-phase mixture? So we learned how to interpolate on different tables for these different properties of water. Now, it's not just water that this works for. This is for any substance that undergoes some kind of phase change, like the refrigerant in your air conditioner, for example. We also started to talk about ideal gases. But first we needed to understand a little bit about compressibility. So that's why we're seeing this compressibility chart here. And we found that we can only really use ideal gases when this parameter, capital Z, the compressibility factor, is approximately 1. And that happens when our reduced pressure is low. So if the pressure is much lower than the critical pressure, we move left on this graph, which gets us close to 1. Or if my reduced temperature is high, so as my TR value gets higher, I get a flatter and flatter curve that's closer and closer to 1. Remember here that this reduced temperature is the temperature divided by the critical temperature. So we're seeing here the numerical or analytical definitions for TR and PR. And when that happens, when my compressibility factor is approximately 1, I can use the ideal gas law. Now, we typically are going to use ideal gas laws with the specific gas constant, where R is equal to R bar divided by the molecular mass, M. And we can use this in several different ways. So we can use this as PV is equal to MRT, or P little v, that's P times the specific volume, is equal to RT. Or we can use it between states, because we know that R is constant. So pressure times specific volume divided by temperature is constant as long as the gas isn't changing. So if there's no chemical reaction, then PV over T is constant. Or because the mass is also constant, pressure times volume over temperature is also constant as I move through processes with ideal gases. If I'm trying to fix states with ideal gases, I have two choices. So I can use specific heat relationships. So in those cases, I'm never going to find the individual specific internal energies. Instead, I'm going to try to find the change in specific internal energy, which is delta U is equal to CV times delta T. Or I can look up properties on table A22 or A22E if it's imperial units, if my ideal gas is air. If not, it'll be a different table in the textbook. So you might get to a point on a test, and I hope this doesn't happen, but you might get to a point on a test where you feel totally lost. If you get to that point, what I want you to do is follow these steps. So look at the type of problem that you have, and if you can, draw a PV or a TV diagram. That might help you understand what table to look at to fix your states. So I think making a state table is a good idea whenever you have a problem that has multiple states, because it's just a one-stop shop, an easy place for you to find the information that you're looking for. If you want, you can also make a process table where for each process, you'll calculate and write down the work in heat transfer that's associated with that process. Then you want to start fixing states. Again, our state table will help here because we know that in order to fix a state, we need two independent intensive properties. And if we look at our state table, we'll see the rows where we have two properties. So that should help us see where we can fix our states. Then we fix our states and we use that information to find process information like work and heat transfer. Remember that in order to find work, we need this relationship PV to some exponent is constant, because then we can use our relationship for work, which is that work is equal to the integral of P dV. Then, when we have all that information, we can put it into the first law. We know our work. We can find delta U because we fixed all of our states, and we can use that information to find the heat transfer. We would repeat steps 4 through 6 for every process until we've completed the whole problem. So how do I use process info? First, I think we have to think about a couple of questions for every process that we look at. We want to ask ourselves, is the process open or closed? At this point, the only thing we know how to work with are closed processes. So we're going to say closed, and that opens up to us the closed version of the first law, which is delta E is equal to Q minus W. Then we'll make some assumptions, typically that kinetic energy changes and potential energy changes are negligible, so our delta E term becomes delta U. So we get that the change in internal energy is equal to Q minus W. Then we'll use some information about the processes. Hopefully, we'll have pressure as a function of volume, and then we can use our equation for work, which is that work is equal to the integral of P dV. We don't have any tables that'll give us capital U because the textbook doesn't know how much mass is in our system. So then our delta U, our change in internal energy, becomes the mass times the change in specific internal energy. Now I got to think, what's in my system? What kind of fluid am I talking about? How am I going to find U or delta U? So how do I define the specific internal energy? And that all comes down to knowing what the fluid is. If it's a subcooled liquid, I can use tables. I can use that delta U is equal to CV times delta T, or I can use that U of a subcooled liquid at a given temperature is approximately equal to UF at that same temperature. If I have a two-phase mixture, hopefully I'm given quality because that makes my life easier. If not, if I'm given something like specific volume, I would use the specific volume to find the quality and then use the quality to find the specific internal energy. If I have a superheated vapor, then if I'm lucky, the pressure and the temperature that I'm given will be right on my table. If not, I'll have to interpolate. So I'll do some linear interpolation. And if I'm unlucky, I might have to do some double interpolation. If I have an ideal gas, I'll say that the change in the specific internal energy is equal to CV times delta T. So then I'm assuming that the specific heat is constant, or that CV doesn't change with temperature. Or if I want a more accurate answer, I can use table A22 and look up the specific internal energies as a function of the temperature of my ideal gas. Finally, after I've done all of that, I know my work, I know my change in specific internal energy, and now I use the first law to find the heat transfer. Then I have to pause and reflect. I say, does it make sense? Does the sign make sense? Hip to win, so heat in is positive and work in is negative. Do the signs that I'm getting in my analysis match my physical understanding of the process? Then, do I say, did my units make sense? Did I carry my units all the way through my calculations? Did I make the conversions correctly? Or am I adding BTU to foot-pounds? So when I was going through our lectures, I realized that we had done an example problem for a closed system where we had water inside our system but not one where we had an ideal gas inside our system. So I wanted to give you one more example here of a first law problem where we have gas inside of a piston and cylinder. So we start at state 1 with a pressure of 80 psi. So that means this is in imperial units. We have a volume initially of 0.1 cubic feet, and our mass is 0.01 pounds. At state 2, we have a pressure of 14.7 psi. That's atmospheric pressure. And we're told for this process, as we move from state 1 to state 2, that P times V to the power of 1.5 is constant. So we do have a relationship between pressure and volume. We're also told that for air, which is what's in our cylinder, the specific gas constant, R, is 53.35 foot-pounds per pound mass Rankine. I'm asked to find, with constant and variable specific heats, the work performed in the system and the heat transferred to the system. So I know that the change in energy in my system is a result of heat coming in or work going out. I'm going to assume that kinetic, potential, and spring energies are all very small compared to the change in internal energy in my system. So I get that delta U is equal to Q minus W. Unfortunately, at this point, I don't know U2, I don't know U1, I don't know Q, and I don't know W. So the good news is that I have an equation. The bad news is I don't know any of the terms inside that equation. So I'm going to start off by trying to find the work. I started with work because I know the integral, or I know the equation here is the integral of P dV, and I also know that for my process, I have a relationship between P and V. So P as a function of V is equal to C divided by V to the power of 1.5, or that C times V to the power of negative 1.5 is equal to PV. So now I can put that relationship into my integral. I know that C is constant, so I pull it out of my integral, and I see that C is equal to the integral from V1 to V2 of V to the negative 1.5 dV. I can integrate here, and after I do that, I see that C times V2 to the power of negative 0.5 minus C times V1 to the power of negative 0.5 divided by negative 0.5 is equal to work. Now, I remember here, I've left this C just as a constant, but I remember that this constant is equal to P1 V1 to the power of 1.5, but it's also equal to P2 V2 to the power of 1.5. So I'm going to match up the subscripts here so that I use, in the first time that I use this constant C, I use P2 V2 to the 1.5. And the second time I use the constant C, I'm going to use P1 V1 1.5. So when I do that, I get P2 V2 minus P1 V1 divided by negative 0.5 is equal to work. So this is good because now I have an equation for the work. I know P2, I don't know V2, I do know P1, and I know V1. So I need to be able to find V2. Now again, I'm going to use the relationship that P1 or that PV to the power of 1.5 is constant. I don't care what the constant is here, although I could figure it out if I wanted to. I'm going to get a symbolic solution for V2. So here I isolate for V2, and I see that V2 is equal to P1 over P2 multiplied by V1 to the 1.5, all to the power of 1 divided by 1.5. I can work this out on my calculator, and I see that V2 is 0.3 cubic feet. So now I can go back to my work equation. I know all of the information here. The one thing I do have to do, so it's always important to carry units in my calculations. If I just wrote the P times V, my pressures are in pounds per square inch, and my volume is in cubic feet. So I'd get this pounds cubic feet per inches squared, which is not a real unit. So now I know that there are 12 inches in a foot, but I want to get rid of inches squared. So my 12 squared times inches squared is up on the top, and I divide by feet squared. I do this for both of my terms, and then I get this number here, that the work is equal to 1,034 foot-pounds. So that's good. I've got my work, and this work is positive. So I know that work in is negative, so this must be work out. So my system must be doing work on the surroundings. Next, we want to apply our first law. So I know that U2 minus U1 is equal to Q minus W. I still don't know U2 or U1. I still don't know Q, but I do know W, so I'm making progress. Now, I want to be able to find delta U. The problem asked me to do this in two different ways. So first, it's going to ask me to assume constant specific heats. Now, whenever a problem says use constant specific heats, it means use CV times delta T is equal to delta U. So we'll do that here. So now my delta big U becomes mass times CV times delta T. I do know the mass. I know T2, or I don't know T2. I don't know T1. I do know CV. So now I got to use the ideal gas law. Now there's a couple different ways we can use the ideal gas law, but in this case, I'm going to look just at state 1, and I'm going to see that P1 times V1 is equal to mass times the specific gas constant times T1. The only thing I don't know in this equation is T1. So I'm going to put all of the information that I know into this equation. Again, I got to recognize that my units here are a little bit weird because I have pressure in PSI and volume in cubic feet. So I got to, again, play around with the unit conversions until things look nice. And now I can put this information in my calculator, and I get the T1 is 800. And I get the T1 is 866 degrees Rankine. Now it's important to realize that this equation, because there's no delta T in this equation, so this equation will always, every time, give me a temperature in degrees Rankine. Or if I'm using it in metric units, it will give me an answer in degrees Kelvin. So whenever I have an equation where the temperature stands alone and it's not a change in temperature, I either want to put in an absolute temperature or I'll get out an absolute temperature. And absolute temperature scales have absolute zero as 0. So now I know everything in my equation that I need to know except T2. So here we'll use the ideal gas law again, but we'll kind of manipulate it a little bit. So if P1V1 is equal to MRT1, but M and R don't change, so M and R are constant. So that means that P1V1 over T1 is equal to MR, but MR is also equal to P2V2 over T2. And here, I don't actually care about the MR in the middle, but I see that P1V1 over T1 is equal to P2V2 over T2. So here, the only thing that I don't know is T2. So I set this equation up as T2 is equal to T1 multiplied by P2 over P1 multiplied by V2 over V1. I know all of this, so I can put it into my calculator. I like to do it this way because here, now, as long as my pressures are in the same unit, so I'm still using PSI here, but because both my pressures are in PSI, the units just cancel out. So this P2 over P1 is actually a dimensionless number. So as long as my pressures are in the same unit, then I'm okay. Same with my volumes. And here I see that the temperature, T2, goes down a little bit to 477 degrees Rankine. So now I know everything that I need to know to calculate delta U. So delta U is equal to M CV times delta T. I know all of this information, and I see that delta U is minus 517 foot-pounds. So this tells me that the energy is decreasing in my system. And I could see that because T1 was bigger than T2, so my temperature is dropping. So now I know delta U, I know W, but I don't know Q. But that's okay, because now I have one equation and one unknown. So I'll isolate for the heat transfer from state 1 to state 2, and I get that this is U2 minus U1 plus W from 1 to 2. I know that delta U is minus 517 foot-pounds, and I know that the work is 1,034 foot-pounds. So in total, I see that the heat, as I go from 1 to 2, is 517 foot-pounds. So heat in is positive, so this must mean that heat is entering into my system. So 517 foot-pounds of heat are entered into my system. So now, how would I do this problem if I was using variable specific heat? So basically the problem would be exactly the same up until the point where I've calculated work. I would come to this point where I say, oh, I would like to find delta U. But now instead of finding delta U as CV times delta T, I'm going to say that there are variable specific heats, so that the specific heat is a function of temperature. And if specific heat is changing with temperature, I can't use CV times delta T without doing some calculus. So instead, I'm going to look up specific internal energies on table A22. Now in this case, because we're using imperial units, we're going to use table A22E. E is for English units. So here's my state table. I used the ideal gas law to find these temperatures and this volume, and none of that is going to change because I didn't have to use CV to get any of that information. So all of that stays the same, and I just have to find U. So this is table A22E. I just took a snip of this. I see I'm going to find the specific internal energy at state 1, where the temperature is 866 degrees Rankine. So here it's important to see that we have temperature in Rankine. So that's in the header for this table. It tells us the temperature is in Rankine. So if you're looking in Fahrenheit, you'll have to convert that using the conversion that's on your exam review sheet. So now I have 866. So that's between 860 and 880. The nice thing about using ideal gases is that the only thing that I need is the temperature. So once I know the temperature, I can fix the state on table A22, or I can use CV times delta T. But in this case, we're using variable specific heats. So now I know, because my temperature is between 860 and 880, that my specific internal energy is going to be between 147.5 and 151. So I need to interpolate. So I get my interpolation factor A. So this is 866. That's the temperature I know, minus the temperature bounds that I have. And this is going to be 6 over 20, or 0.3. And then I use that interpolation factor in this equation. So this is now going to be my minimum value of U plus A times delta U on my table. I work this out and I get that U1 is equal to 148.6 BTU per pound mass. So I put that up on my state table. Now I want to find specific internal energy of state 2. So I'm going to do the same process, but now my temperature is 477 degrees. So I look here, 477 is between 460 and 480. I'm going to use a different interpolation factor, B, and that interpolation factor is 17 over 20, or 0.85. I put that into my expression for the specific internal energy as I'm interpolating with this factor B, and I find that U2 at 477 degrees is 82.37. So I do notice here that U2 is less than U1, and that's encouraging because when I did the problem with constant specific heats, I found that delta U was negative. Now the magnitude's different here. So here I can see that my delta U is equal to mass times the change in specific internal energy. I can rearrange for Q, because Q is the thing that I don't know here. So Q is equal to M times the change in specific internal energy plus the work from 1 to 2. That equation now came up here to the top. And now hopefully I have all the information that I need. So I know the mass, I know the change in specific internal energy, and I know the work. So when I work this out, I get to this problem. So before, I saw that my delta U was something like minus 500 and something when I was using constant specific heats. And here it says it's minus 0.66. My work is still 1,034. And if I wasn't tracking the units in my calculation, I would probably, or at least potentially, make a really big mistake here. But here I see that it makes no sense to add British thermal units, or BTU, to foot-pounds. So I have to convert BTUs to foot-pounds. And this is really weird. Like, this is another thing that, if you don't love the metric system yet, you certainly will after you do some more imperial problems in this class, because these conversions make no sense. There's 778 foot-pounds in a British thermal unit. So that's what we have to do. We're trying to get rid of these British thermal units. So we put British thermal units here on the bottom, and there's 778 foot-pounds in a BTU. So now my BTUs will cancel. Here again, I can do some math so that I can be adding apples to apples here. And I get that negative 515.3 foot-pounds plus 1,034 foot-pounds is equal to Q. So here now I'm starting to feel better about this answer, because once I've converted the units, my numbers are starting to look the same. I find when I'm using variable specific heats that Q from 1 to 2 is 518.7 foot-pounds. I think we had something like 517 foot-pounds for constant specific heat. So this makes me feel really good, because I got basically the same answer when I did the problem in two different ways. Again, I see that heat in is positive, so heat must be added into my system in this process. So hopefully, after you see this review and a problem like this, where we did an imperial problem, where we had to play around with units, and we used an ideal gas, so hopefully after doing this, you feel pretty confident headed into the first exam. Good luck, and I'll see you next time on Thermodynamics.